Hello, Algebra 2. How are you doing? Hopefully well. We're going to just take today, this first assignment. It is week 5. It's assignment 1. It's 5.1. We're just going to take this day and do a little review. We've been talking about a lot of stuff, and we're not there in the classroom, so I can't answer everyone's questions, so we're just going to take a step back, talk about a lot of things that we've covered. Let's just start real quick and remember what direct versus inverse variation, say that 5 times fast. What exactly the difference between these two are. Direct, right? There's always, for all these, there's like a variable y, variable x, and then a constant of variation, which we usually call just a, right? It's our constant, our parameter. Direct variation looks like y equals a times x, and this was always what we called like linear, right? It was just a line. Some examples of direct variation would be maybe y equals 4 times x. Again, here my constant of variation would be 4. What about y equals 1/2 times x? Again, my a value here would be 1/2. I'm multiplying by 1/2 there. Whoops. What about y over x equals 6? All right, it doesn't look like direct variation right now, but I can do a little bit of algebra. If I multiply by x on both sides, right, that x over here and the x over here is going to cancel out, and I'm just left with y equals 6 times x, and yeah, that is direct variation. All right. We also talked about inverse variation, which kind of led into our topic of rational functions. So inverse variation looks like this: y equals a over x. And this is, again, what we're starting to call rational functions. Again, if you ever think about rational numbers, you should be thinking about fractions, right? So, and I mean, we see fractions right here. That's why we call them rational functions. Some examples. Here's my examples of inverse variation. We could have y equals 9 over x. Again, our a value here would be 9. We could have y equals 5 over x. That's an example of an inverse variation with our constant variation being the number 5. What about y times x equals 3? And if you remember when we talked about in our, I think it was maybe 2 weeks ago, we talked about if you multiplied your two variables together, you should get a constant, and that was like a key feature of inverse variation. And here I am multiplying my two variables together, and I'm getting a constant of 3, so this would be inverse variation. Again, I could use a little bit of algebra like I did before to rewrite this into this form, like what we're kind of used to with inverse variation. So right here, I could let's just divide by x on both sides to solve for y. That x is going to cancel out over here, and I'm just left with y equals 3 over x. And hey, that is a inverse variation like form, right? Okay, so we talked about inverse variation. Let's remember rational functions. Again, we're always going to start with like our parent function of 1 over x. And since we have, we could also do this like transformations. Sorry, I wasn't remembering where I was going with that. We do transformations. So if this is like f of x equals 1 over x, maybe you've got some transformations. So function g of x, you could say a times, again, we're kind of using this form, x minus b on the bottom plus c, or I'm going to move that, or you could do a over x minus b plus c, right? These two forms are the exact same thing. All I did was I just took that a value and multiplied it through that fraction, so now it's on the top, all right? And these were our kind of basic forms for being able to graph these, and I'm going to bring that back real quick. So, oh, not a highlighter. Oh, no. Oh, no. Hang on. So here's my little graph, all right? If we wanted to find a vertical asymptote, let's say that we had an example of f of x equals 1 over x plus 3 plus 5, right? If we wanted to find a vertical asymptote, again, those steps were to set your denominator, I'm going to just abbreviate it like that, set your denominator equal to 0 and solve for x, all right? So here my denominator is x plus 3. If I set x plus 3 equal to 0 and solve for x, I'm just going to minus 3 from both sides. X equals -3. That means I have a vertical asymptote, again, vertical going up and down, a vertical asymptote at x equals -3. So maybe this is -1, -2, -3. Here's my vertical asymptote kind of going like this, all right? And then my horizontal asymptote, the horizontal asymptote really just comes from this vertical shift on the outside. So it's whatever number you're adding onto the outside, that's your vertical asymptote. So really it's just as easy as saying, well, y, again, sorry, this is all horizontal asymptote. Your y value is equal to whatever you're adding onto the outside. So here my y is just equal to 5. And I could draw a second asymptote of horizontal one. So I could go up 5, maybe 1, 2, 3, 4, 5, and say that I have a horizontal asymptote there. And then I could sketch my function. I'll do the function in green. And the parent function, right, the parent function looked like this, where we had horizontal and vertical asymptotes at x equals 0 and x equals 0 and y equals 0. Here, the thing just shifted, so it all looks very similar. It just shifted up, all right? So for today's homework, I'm gonna be asking you, I might have you like graph one of these things, but I'm gonna ask you to write, given a little transformations, I'm gonna ask you to write a function, basically a rational function. So if I told you that a rational function has a vertical asymptote at x equals -2, let's just start real quick with our parent function, right? I know that I've got 1 over x. And again, when we were looking at horizontal asymptotes, we set that denominator equal to 0 to solve. So there's something in my denominator that I set equal to 0. Let's just see if we can get this x equals -2 equal to 0. So I'm just gonna add 2 to both sides, right? Because that's gonna cancel out my -2 on the right-hand side of my equation. So if I add 2 to both sides, that cancels out, and I'm just left with x plus 2 equals 0, and my x plus 2 has to be my denominator of my rational function, all right? So this parent function, I'm just going to extend that line and say that my denominator is x plus 2. That is what would give me a vertical asymptote at x equals -2. And let's graph that real quick, just a sketch of it. I have a vertical asymptote at x equals -2, so I'm going to just, add my little dotted line for my asymptote. Again, asymptote is a line that my function, or, that a curve or a line, it's going to approach, but it's never going to cross or meet that line, right? So x equals -2, and then my function here, again, we don't have a horizontal asymptote, so we're just going to keep it at y equals 0. And there you go, that looks pretty close. There you go. All right, very nice, very nice. And if you wanted to check, right, we could plug that value of x equals -2 into my function, right? If this is my function that we decided on, if I plug x equals -2 into here, I would get 1 over -2 plus 2, and that would just cancel out and be 0. 1 over 0. Again, can you divide by 0? No. That's why we have that vertical asymptote at x equals -2, so that checks out. Let's do another one real quick. If you have a vertical asymptote at x equals 3 and a horizontal asymptote at y equals -4, let's just add those sketches into our little picture here. My horizontal asymptote at -4, y equals -4, and my vertical asymptote at x equals 3. Again, let's focus on that vertical asymptote. I think that would be the hardest part. X equals -3. There you go. So vertical asymptote again, something in the denominator of my function that I have to set equal to 0. So we're just going to do a little algebra over here in order to get it set equal to 0. So I'm just going to -3 to cancel out that 3 on the right-hand side of my equation. That's going to cancel, and I'll just be left with 0. X minus 3 equals 0. So that x minus 3 expression right here, that has to be the denominator of my equation. All right, so currently I have 1 over x minus 3. That takes care of the vertical asymptote part. What about the horizontal asymptote? I have a horizontal asymptote at y equals -4. Again, just like what we said above, that horizontal asymptote, it's really just a vertical shift. So I'm just going to throw that -4 onto the end and say -4 there, all right? So there we can see our vertical asymptote. Here is our horizontal asymptote. We've already got the asymptotes sketched out, and then I can just graph this thing, give it a little sketch here. Again, we're just starting with these very basic ones today, and we'll get a little more complicated later, all right? So there would be a good sketch of it, and you have your function. So I could even, let's just put a function name, f of x equals 1 over x minus 3 minus 4. Okay, the last one has a horizontal asymptote at y equals 6, and it is vertically stretched by a factor of 3. I'm going to scroll back up to the top real quick so we can see that like basic form with all of our transformations. Okay, this part right here. So this x minus b, again, that is our vertical asymptote. That's going to identify our vertical asymptote. The plus c helps identify the horizontal asymptote, but that a here, or the a over here, that again is our stretch or compressions vertically, all right? So again, that a value is just like a scale factor technically, right? So horizontal asymptote at y equals -6, again horizontal, so it's really just kind of like being added onto the end, right? So if I start with 1 over x, I'm just adding 6 to the end for that horizontal asymptote, vertically stretched by a factor of 3. So then I'm just multiplying my parent function, right? This kind of like inside thing, I'm just multiplying that by 3, and that's going to vertically stretch it. Again, this is your vertical shift, right? Just shifting up and down. But when we're multiplying, we're just multiplying to that original part, if that kind of makes sense. So you could write your function as 3 times 1 over x plus 6, or you could write it as 3 over x plus 6. Either way works. It's totally fine. Again, if we had to sketch this, let's just sketch it real quick. I know I'm going to have a horizontal asymptote at y equals 6. But I'm still going to have a vertical asymptote because, again, we can't divide by 0. If I set that denominator of x equal to 0 and solve for x, well, again, it's already solved for, I'm still going to have a vertical asymptote at 0 because even though there's nothing down there, right, you still can't divide by 0. You have to check for that vertical asymptote. And then stretching it by a factor of 3, I'm just going to try and draw it a little bit stretched out. That looks a little stretched out. Anyway, it's just a sketch. We got a rough idea of it. Fantastic. You guys are doing great hanging there with me. So those are some examples that I might ask you. I might give you some details about a rational function. I'll ask you to write the function itself. Okay. And then just from a graph, can you identify what the vertical asymptotes are and write them in a function? So with this thing, just looking at it, here's my x and my y-axis, all right? So orientate yourself with that. Here, I can see if I look vertically, it looks like I've got some sort of vertical horizontal asymptote at y equals, and what value is that? It's looking like y equals -6. And I think it looks like I've got a nice horizontal asymptote. Again, this thing has been shifted. So a horizontal asymptote, I did it again. A vertical asymptote at x equals 5. So if I have to put that all into a function, I could say this is some sort of function, f of x equals, what is my denominator going to be, right? Look at that horizontal asymptote. If I've got x equals 5, how would I figure that out so it's set equal to 0? Well, I'm just going to -5 from both sides, and that gets me x minus 5 equals 0, right? Those cancel out. So now I can see my denominator, it's set equal to 0 here, right? My denominator has to be x minus 5. And then my horizontal asymptote, the y equals -6, I'm just going to add that onto the end there as -6, that horizontal or vertical shift down, excuse me, there would be my function, all right? One more, again, we'll just identify a quick horizontal asymptote. Okay, so it looks like there's a line that it's kind of approaching but never touching. And I'm going to say that it's not 0 and it's not 1 here, but it's pretty close to about 1/2, right? Right in between 0 and 1, so f of x equals 1 over something plus 1/2. All right, I threw a fraction in there. So my horizontal asymptote would be at y equals 1/2, and that would indicate my c value that's being added onto the end. And then a vertical asymptote here, it's looking like x equals 2. We agree with that, or -2, excuse me. I have a vertical asymptote at x equals -2. Again, how would we get this thing equal to 0? Let's just add 2 to both sides. And then I have x plus 2 equals 0. There would be my denominator of x plus 2. All right, there you go. Wonderful, wonderful. Thank you guys for watching. If you're here this far, please enjoy this very cute video of my aunt's dog, Henry. Very cute, very adorable. And I think I'm done talking for today. All right. Have a great day, guys. Go team!